differential equations. Are we ready? Okay, here we go. Okay, Euler's method. Euler's method to numerically solve differential equations. The reason we have to have a numerical way for solving differential equations is not all differential equations are solvable, you know? And now don't write this down, this is just intro, but you know, we've got a situation where if I have dy dx equals y, hey, you can solve that because you can get the y on one side and have your dx on the other. Or if I had dy dx equals, you know, x plus 2 times y minus 3, you know, well, the same thing. You can get your y's on one side, you can get your x's on the other side, and you can take the antiderivative of both sides. But what happens if you get something really, really complicated that you can't separate? What if I have something like this, dy dx equals the log natural of x plus e to the y minus the inverse tangent of xy? You know, I get something crazy like that where there's no way to separate the x's and y's. I can't get all my x's on one side and all my y's on the other side multiplied by dy. It's not possible. And it may be that I can't solve this at all. There's other techniques for solving differential equations, and I might not even be able to use them. So what do I do with a differential equation that I can't solve analytically? And the answer is you're going to have to solve it numerically. You're going to have to solve it by plugging in numbers. It's kind of akin to that algebra problem where you can't solve for x. So the only way you can get the answer is to just plug numbers into your calculator until you get lucky and find the answer. And that's kind of what we're doing here, only it's with a differential equation. And this method of numerically finding the answer, just plugging in numbers till I get the answer, that method is called Euler's method. So let me show you where Euler's method actually comes from. Okay, and in order to teach you Euler's method, I can't start you with one of these really, really hard ones. I got to start you with an easy one just so you can learn Euler's method. So we're going to start off with one of the easiest differential equations I can think of, which is dy dx equals y. Okay? And we're going to let y of 0 equal 1. That is, when x is 0, y is 1. So that's the initial value of my differential equation. Okay? And let's say I don't want to find an equation that gives me all the answers. Let's say I'm only interested in one particular answer. I just want to know what y of 0.5 is approximately. You see? So I don't need an equation for the solution that gives me what y is for any x in the whole universe. I just want to know what y is specifically for 0.5. Okay? Well, here's one way I can do it. Let me show you. Here's 0. And here's my initial point 1, correct? 0, 1. I could just pretend, I don't know what the solution to this guy is going to end up being, what sort of crazy formula, but let's pretend that a line is a nice approximation. That is, you know, it's true that any curve I were to give you, for a small neighborhood of the curve, the tangent line is a nice approximation. Now, the tangent line isn't a good approximation as you get far from this neighborhood, but for any neighborhood of a curve, a linear approximation is a reasonably good approximation. So here's what I'm going to do. I'm going to say, hey, I don't know what my curve actually does, but I'm going to get the equation of the tangent line at x equals 0, and then just ride that tangent line until I get to 0.5 and say that that's approximately my answer. So let's get the equation of the tangent line. Get the equation of tangent line at x equal 1. Well, I'm sorry, at x equals 0. Well, you know you need two things for a tangent line, right? The point and the slope. I got my point, 0, 1. I got my slope. You tell me, what's the slope of this tangent line going to be? Yeah, Kylie, how'd you know it was 1?
Because it's equal to 1.
Yeah, good for you. So there it is. I got my point and my slope. My point is 0, 1, and my slope is dy dx, which in this case is equal to 1, the y value, okay? So I can now make my tangent line. Here's my tangent line. The slope is equal to 1, correct?
Yeah.
And so if I approximate my curve as actually being the tangent line, some of you are really good enough at math to tell me, what is that y value going to be? If my slope is 1 and I go and I run 0.5, what's my rise going to be? Yeah, this guy's going to be 1.5 because my rise is going to be 0.5, right? So I just did a linear approximation. I say that y of 0.5 is approximately equal to 1.5, okay? And in some cases, that might be good enough. Just getting the linear approximation and approximating the answer is often good enough. And in this case, if I were to solve this equation, and I'll just tell you right now, the equation, since that is a what do you call it? That's going to be an exponential growth thing, dy dx equals 1 times y. So the solution ends up being y naught times e to the 1 x, which in this case my y naught is 1. So I get y equals e to the x. So the true solution is e to the 0.5, which ends up being, here's a second, clear, e to the 0.5, 1.65 approximately, 1.648, okay? So this is the true solution, the solution that we don't have available to us if the differential equation is not solvable. But in this case it is, so we get the true solution. But this solution might be close enough. But what if it wasn't close enough? What if I wanted to get closer? Then you do Euler's method, and here comes Euler's method. Here comes the theory behind Euler's method. What you do is, rather than choosing that tangent line and writing it all the way over 0.5, you choose this tangent line and only write it over for a distance of 0.1. And then at this point, you recalculate the slope of the tangent and write a new tangent line. You look at this guy and get a new slope. You say, hey, whatever my y is, I'm going to plug that in, get a new slope, which, by the way, that new slope is going to be higher, right? This slope, the slope is 1 because the y-coordinate is 1. Here, the slope is going to be slightly higher, and you ride that new slope until you get to 0.2. And then recalculate your slope again and get a new line, a line with a new slope, in this case a bigger slope. And you ride that line, that tangent line, until you get to 0.3. And then you calculate a new slope till you get to 0.4 and a new slope to get to 0.5, and you end up, your linear approximations end up hugging the true solution a little bit better than that initial linear approximation did. So that's what we're doing. We're doing linear approximations, but we're changing the slope every so often so that my linear approximations end up hugging the original solution a little bit better. That's all the theory behind it. Okay, it is now time for me to teach you how to do it. Here we go. Let's approximate y of 0.5 using Euler's method with 5 intervals. I'm going to put you one. So here's what you're going to do. You're going to have x. You're going to have y, and make y pretty wide. And then you're going to have delta y, which is equal to the slope times delta x. Those are the three columns you're going to have. I want to remind you, for this problem, dy dx is equal to y, and remember, that's my expression for the slope. I have an expression for the slope. It's dy dx, which is equal to y. Next, you're going to start with your initial point. My initial point is x is 0 and y is 1. And then you're going to get how much you're going to go up, how much your y increases on this one line. And remember, slope, slope is equal to rise over run, right? And rise is equal to delta y, and run is delta x, the change in y over change in x. So do you agree that slope times the change in x is going to equal the change in y? Okay, so that's how I'm going to get my change in y. I'm going to get how much up I have to move. My slope is going to be 1. My change in x, because I've chosen 5 intervals, my change in x is going to be 0.1. I'm always going to be going over in increments of 0.1. Why 0.1? Because I'm trying to find y of 0.5, and I decided randomly to choose 5 intervals. So my delta x is 0.1. So I get a delta y of 0.1. Which means when x is 0.1, because remember how much I'm increasing x is what my delta x is, which is, I have 5 intervals. My new y is going to be the old y plus the change in y, 1.1. That is, what happened here is I had a run of 0.1, I had a slope of 1, which meant I had a rise of 0.1. So now I'm right here at 1.1. My approximation of y of 0.1 is 1.1, and now I'm going to find my new slope, the slope at 1.1. So my delta y is going to be the slope. The slope is y, which is 1.1, times the delta x, which is 0.1. It's going to be 0.1 for every interval. And so I end up with 0.11. So now, on this green guy, my delta x is 0.1, but my delta y is a little bit bigger because the slope is a little bigger. The slope is 1.1. So my delta y is 0.11, meaning this point here ends up being 1.21, right? If I'd stayed on this blue line, it'd just be 1.2. 1.1, 1.2, 1.3, 1.4, 1.5. But I'm not staying on the blue line anymore. I'm recalculating my slope every interval of 0.1. So now this guy here, when my x is 0.2, I'm at 1.1 plus 0.11, which is 1.21. Believe it or not, it's your turn. I'd like you to please get this delta y and then get the next point. Please do that now. And we'll do it again and again, and I'll give you another example. And then, Okay. Well, hey, let me do this next one. Are you guys okay that the slope now is the y-coordinate, which is 1.21? Which means when I multiply by 0.1, I get 0.121. You guys okay with that? So when this is 0.3, I add 0.121 to this guy, and I get 1.331. How many people got 1.331 for this guy? Okay, yay for all of you. Let the video record reflect that almost everyone raised their hand. You guys okay with 1.331? If you didn't get it, that means you did bad adding. And that's okay. Okay, well then I'd like you to please keep going until you get to 0.5. Let's see if we agree on what 0.5 is, and I'm going to do it myself. By the way, there's no quick way to do this. Well, I mean, well, there kind of is, but no, not really. So I got one, whoops. I got to go to 0.4 now. So 1.4641. It's looking like the old Pascal's triangle. 61051. And there you go. It turns out the true answer was 1.648. If I just did a linear approximation, I get 1.5. But if I do Euler's method, I get 1.6105. So that's better, right?
Yes.
Heck yeah. Okay. Hey, you guys ready to do one on your own?
Yeah.
Good, that's what I like to hear. I heard one combination yawn yes, and that's good enough for me. Oops, I didn't mean to do that. Here we go. For the differential equation dy dx equals negative x over y, where y of 0 is equal to 1, approximate y of 1 using Euler's method and 5 intervals. Good luck. I'll give you a hint. Please set up this chart and put your initial point there, and then we'll see if you can get the next point. What are you guys getting for delta x? What's my delta x in this situation? Good, you guys getting 0.2? Because you're going to go from 0 to 1 with only 5 intervals. So that's 0.2 per interval. So that was an important thing for you guys to get. How many people got that the next y is going to be 1 also? Good, good for you guys. That's the way it is. Now go ahead and get the next one, 0.4, and then I'll just keep going myself. Is that right? Anyone get 0.96 for the next one? Oh, yay. Okay, good. All right, and then, hey, keep going. And at some point, you're going to have to use your calculator, obviously. I'm actually going to do it on my calculator where I don't have to round. So the slope is 0.8 divided by that answer times 0.2 plus that answer. I end up with 0.52. So any questions or issues on the Euler's method? Euler's method is really good if there's only one particular value or a small set of values you need to get. Then Euler's method is awesome. Tell me, if I wanted to get a more accurate measure of what y of 1 is, how could I do that? Say again? Yeah, more intervals, right? If my, this guy ends up being a circle, okay? And so I'm writing these tangent lines, and with each tangent line I get farther and farther from the circle. Well, if I had 1,000,000 intervals, then I'm pretty much hugging the circle, and I'm gonna get exact. Okay, good. And we'll talk more about error tomorrow.